Hello, everyone, and thank you very much for participating. We are really excited for today's topic, near-Earth asteroids from danger to utilization. Before I introduce our speaker today, engineer consultant Werner-Grandl, I would like to remind everyone that this webinar is an educational material preparing for the uh, event that we are organizing, which has the title "Expanding Humanity to Outer Space: International Cooperation." Of course, it's targeted to the youth, and also we are thanking Adriano, who is supporting with the logistics during this webinar.
Hello, everybody.
Yeah, so introducing the speaker. So Werner-Grandl is a consulting engineering, and he was born in March 31, 1957 in Vienna, and later pursued a degree in architecture from the Technical University of Vienna, graduating in 1984. Following completion of his academic journey, he took on military service in the Austrian Air Force in 1985. Subsequently, from 1986 to 1993, he gained practical experience working in various engineering offices. In 1994, Werner-Grandl transitioned into the role of freelancing architect and consulting engineer, a path he has successfully navigated ever since. However, his professional journey is marked by more than just architectural pursuit. Since 1987, Grandl has been deeply engrossed in studies revolving around space stations, space colonies, and the utilization of asteroid resources. A notable contributor to the field of space exploration, Grandl's impact extends through the publication of several books and papers. One such significant work was presented at the 11th SSI Princeton Conference in 1993, titled Space Manufacture 9, The High Frontier, Session Development and Utilization. Under the heading Astropolis, Space Colonization in the 21st Century, co-authored by Antonio Germano. Additionally, his contributions span a wide array of topics, including commercial asteroid resource development, lunar base design, and the exploration of near-Earth asteroids. Residing in Tulln, Austria, Werner-Grandl continues to be steadfast presence in the realm of space architecture and exploration. Grandl's enduring commitment to advancing our understanding of space and its potential applications underscores his status as a prominent figure in the scientific community. So, our second webinar today, title is Near-Earth Asteroid from Danger to Utilization. And of course, we are inviting the youth to understand more about this topic, because it will be extremely important for them to utilize the knowledge and concepts of today's presentation in the event. Maybe this will be helpful for them to win the first prize. So today's presentation, today we'll discuss the utilization of near-Earth asteroid for mining and building human habitats inside of some of those celestial bodies. Near-Earth asteroids, which are expected to contain resources like nickel, iron, platinum group metals, or rare earth elements, and have a minimum density of 2 grams per centimeter cubic, and a diameter of 1 to 500 meters, will be selected for mining. We calculate the energy which is necessary to modify the orbits of NEAs by orbital maneuvers from their solar orbit to Earth orbits. To move the NEAs by remote control, unmanned space tugs with advanced propulsion system were designed. A pair of tugs is docked to the asteroid using drilling anchors. The rocket engines of the tugs then apply the thrust forces for the maneuvers. Once stabilized in Earth orbit beyond the Moon or in the Lagrange point L5 or L4, the mining process is started along the major axis of the asteroid. A manned space station will be connected to the asteroid, carrying digging, conveying, and processing machinery in the storage module. A tunneling machine initially digs a central tunnel of 8 meters in diameter to the center of the asteroid. Then a spherical cave up to 50% of the NEA's volume is excavated. When the mass of the asteroid decreases constantly, the orbital position is stabilized by the two space tugs. The processed material is either used for industrial production in L5 or transported to low Earth orbit. In the last phase of the mining, the inner surface of the cave is centered by a robotic laser device. After the end of the mining process, a rotating human habitat can be built inside the cave to simulate artificial gravity. The remaining shell of the asteroid will provide shelter against cosmic rays, solar flares, and micrometeoroids. The various materials produced by asteroid mining can be used for construction, and oxygen, hydrogen, and carbon can be extracted from other carbonix asteroids. We propose to construct a prototype asteroid habitat in L5. Natural sunlight is collected outside the asteroid's shell by parabolic mirrors and beamed into the cave through the central tunnel. Urban gardening and aquaculture provides nutrients for approximately 2,000 inhabitants. This is, of course, extremely exciting. Our second webinar will be the fine line between science fiction and real science. So, Werner, the floor is yours.
Okay, thank you very much for your introduction, which was nearly as interesting as my speech now will be. So once again, hello everyone, and thank you for having me. And of course, today we are talking about near-Earth asteroids, or NEAs. Some of them can be a real threat to life on Earth. An astronomer called Paul Abel has said 1 year before, you can't choose the asteroid chooses you, if it is dangerous, if it is a dangerous one. Now the number of detected NEAs has increased dramatically in the last 10 years. On the left side, you see the number of NEAs in the year 2014 by NASA, and it is about 12,500 objects in total, and from those were approximately 1,000 objects larger than 140 meters in diameter. On the right column, you can see the known NEAs last year. Now we have approximately 32,000 objects in total, and from those are about estimated about 10,000 objects larger than 140 meters in diameter. So this is a very large and a very big number of near-Earth asteroids, which can sometime become very dangerous to Earth and to life on Earth and to human civilization. Now the near-Earth asteroids family. There are 3 categories of near-Earth asteroids: the Apollos, the Athens, and the Amors. The Amors are crossing Earth at approximately 1 astronomical unit. 1 astronomical unit is the average Sun-Earth distance of 150 million kilometers. The Athens asteroid can sometimes cross Earth if their orbit around the Sun is maybe disturbed by Jupiter or other big planets. But of course, we will focus on the so-called Apollo asteroids. So, next slide. Just a moment. I have to look for a paper. So, what are the so-called potential hazardous asteroids, or PHAs? Asteroids which come closer than 7 million kilometers to Earth are called potentially hazardous asteroids, or PHAs. The velocity change for a spaceship is below 12 kilometers per second to reach those PHAs. Of course, PHAs with more than 140 meters in diameter will maybe deserve a nuclear blasting charge for deflection. What you can see in the figure below, you can see that there are about 10,000 PHAs between 100 and 500 meters in diameter on the right side. But also, for example, there may be about 12 objects or about maybe 15 objects with 3 or 4 kilometers in diameter. This is, of course, a very rough estimation. But you can see how high is the number of near-Earth asteroids and also of potential hazardous asteroids. Now I show you a picture of the known impact craters on Earth. In recent years, many impact craters have been found on Earth. Most of them are very old and are covered with layers of younger material. So next slide. Up there. Problems with my computer. Now, okay. So what asteroid science will we do and can we do? First of all, we have to try to detect many of them of unknown asteroids, and then we will have to calculate the angular velocity, and then we have to calculate the apparent magnitude of them, and we have also to determine the rotation period, because most of them are rotating asteroids. We do this research with a number of telescopes, mostly robotic telescopes, around the globe. And the reason is the more of them, the more of robotic telescopes we use, the more precise are our calculations, of course. So we have telescopes based in Australia, in Chile, in Spain, in Canada, in Hawaii, of course, which is the most known one, in Australia, and so on. So this is the machinery to calculate and to detect the course of near-Earth asteroids. So the majority of asteroids, as we know so far, are so-called rubble pile objects. They are a conglomerate of boulders and stones of different sizes. I have shown the data of two examples. The first one is Apophis, which is encountering Earth in the year 2029 at a minimum distance of 31,000 kilometers. So this is very, very near to Earth. Apophis has approximately 370 meters in diameter, and it is a rubble pile asteroid. So the second one I have mentioned is the asteroid Bennu, with a diameter of approximately 525 meters. It's also a rubble pile asteroid. So the next slide. For example, if Apophis will encounter Earth in the year 2029, how could we gain asteroid material from a rubble pile layer, e.g. from Apophis? I think we could send an interceptor rocket to change the trajectory of the asteroid by a kinetic impact. If we calculate the maneuver carefully, we could force the asteroid in a lunar orbit. It is seen on the left side here. The asteroid would break into pieces and become a ring of material around the moon, like the maybe like the ring of Saturn, or a similar planet. So next slide. Asteroid mining, the challenge of the future. What geochemical types of asteroids are there in the universe and in the solar system? In the table, which is shown here, you can see some mineral associations of elements. For a future space industry, I have underlined the most important ones, such as iron, nickel, gold, platinum, silver, aluminum, and so on, titanium, and of course, rare earth elements. Now, how to use these resources for the benefit of mankind? The first step is, of course, always sending robotic probes to near-Earth asteroids, and preferable to potentially hazardous asteroids. So, next slide. What to do with really hazardous asteroids? We could deflect them, for example, by a kinetic impact, or if it is a bigger one, bilateral nuclear detonation, the nuclear blasting charge, or also a chemical charge of blasting. But the smartest method, in my opinion, would be to connect rocket engines to the asteroid. If we have enough time to do so, of course. Then we could modify the orbit of the asteroids from solar orbit to Earth orbit or lunar orbit. From current solar orbit to a stable orbit beyond the moon by connecting space ducts with advanced propulsion systems to catch and guide the asteroids. Maybe this is a little bit science fiction, but we can work on this in the next decades. Now you can see here a schematic drawing how to change the course of a hazardous object. The asteroid's original orbit around the sun is in red. You see here the sun, and this is the original orbit of the asteroids. And there is, of course, the danger of a collision with Earth. The orbit of Earth around the sun is shown in blue. This is the blue curve. This is Earth, of course, and this is also Earth 1 year before. When the asteroid is encountering Earth, the space tugs are launched. After the rendezvous with the asteroid, they prepare for the maneuver. So they have enough time. There are several months to prepare. And after several months before the next encounter to Earth, the rocket engines are fired. The new course of the asteroid is shown in green. The asteroid is forced into an Earth orbit. If possible, it is caught in a Lagrangian point of the Earth-Moon system. This would be the optimal solution. Here, a detailed sketch where I have tried to show the arrival of the asteroid. We can also use a so-called swing-by maneuver using lunar gravity. So the maneuver can be assisted by a lunar swing-by, so-called gravity assist. And now the asteroid is forced into an Earth orbit near the moon. Or, of course, it can be caught in a Lagrangian point of the Earth-Moon system. This is the optimum solution. It would be, of course, the optimum solution. When the PHA has arrived in a near-Earth orbit, it is forced into a stable Earth orbit beyond the moon or in a Lagrangian point. This is the optimum solution. So, if we choose an asteroid for orbit modification and mining, it needs at least a bulk density of 2 or 3 grams per cubic centimeter, because otherwise it is a rubble pile asteroid. We take, for example, the asteroid 2008 EB5. It has a diameter of 450 meters and an estimated mass of 143 million tons. This is in kilogram, but it can also be expressed in tons. And it has approximately 143 million tons of mass. The spectral type, the so-called spectral type, is F, which means that it is a stony asteroid. So, next slide. Okay, this is now a little bit of mathematics. Now we need the transfer energy, the so-called transfer energy, to change the current solar orbit of the asteroid into an Earth orbit. So I have developed those equations together with the Institute of Astronomy of Vienna. So this is very, very good proof. So we take the difference in the so-called Kepler energy between the asteroid's current solar orbit and the Earth orbit. It is an equation which is from Roy from the year 1988. So, okay. At the end of the equation, the required transfer energy is approximately 2.8 exajoule, what is about 2.8 million terajoule. So this is, of course, a very, very huge energy. Next slide. So we need, of course, for this reason, an advanced propulsion system, for example, the so-called Bussard fusion engine, which has been developed by Robert Bussard in 1997 and in the year 2002. So this is his last publication, as I know so far. It is also called the quiet electric discharge engine. Now, this engine is a rocket engine, of course, where deuterium and helium-3 are fusing to helium-4 plus protons. And the protons release an energy of approximately 18.3 mega electron volt, which is very, very huge. For the deuterium helium-3 fuel, Robert Bussard gives a specific energy of 3.5, 14 power of 10 joule per kilogram, which is very, very high. So now for our asteroid maneuver, we can compute the required fuel mass, and at the end of the equation, we need 8 tons of fuel, which means 8 tons of helium-3. Now, helium-3 can be found on the lunar surface as a product of the solar wind. Helium-3 is let me see, abundant on the lunar surface as a product of the solar wind for many millions of years. And of course, this is one of the reasons, the main reasons why we must return to the moon. Of course, to harvest also this helium-3 fuel. So the next. Okay. Here you can see a preliminary design of asteroid space duct with Bussard fusion engines. They are all built of modular cylindrical modules with a length of 24 meters and 8 meters in diameter. They have all drilling anchors so they can be fixed to a celestial body like an asteroid. And of course, they can change their shape by hydraulically and by so-called turning points. And so it may function. The tugs can apply forces in every direction. As you see, F force, 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 force. This is the flight track. This is the center of gravity of the asteroid. And the space tug number 1, which you can see here on the left side, only adjusts the flight track, and the tug number 2, the space tug number 2, applies the primary forces for the orbital maneuvers. So they two space tug can guide the asteroid through space. So what's next? Once stabilized in an Earth orbit beyond the Moon, the mining process is started along the major axis of the asteroid. You see here the asteroid's crust, and along the major axis, the mining process is started. A manned mining station is docked to the asteroid, and a tunnel boring machine is excavating a tunnel of approximately 8 meters in diameter to the center of the asteroid. You see some material processing units. You see storage units for the processed materials. And you see, of course, last but not least, a small rotating habitat module for the crew, for the mining crew. So, what's this? Now, what are the advantages of an asteroid's Earth orbit? Of course, a short flight time from Earth, 5 to 7 days, and the rate of mining advance, removal of ore and storage can be kept equal to the rate of cargo shipping. Then, after the mining, the hollow asteroid can be used as a shelter for industrial facilities or for storage, water, oxygen, etc., for space industry. And then asteroids with more than 400 meters in diameter can be used for rotating human habitats with artificial gravity, because the remaining stony crust provides shelter against cosmic rays, solar flares, and meteorites. So this is our goal. Now we can design a rotating habitat inside the hollow asteroid. We construct a torus of 250 meters in diameter. So you can, in the section, you see a section of the whole torus. It's about 250 meters in diameter. The torus is driven by magnetic levitation. You see here the magnetic levitation bearings. You can compare it to the, as you know, the facility on the Moon, which was designed by Gerald O'Neill which is built on the same principle. Whilst the asteroid itself remains non-rotating, if the asteroid would rotate also, it would soon crumble into pieces. So it has to be stable, and only and just the interior torus has to rotate. The rotation rate is about 3.5 rounds per minute. It simulates about 90% of the Earth's gravity. On the inner surface of the torus, we have housing, we have the living area, we have housing for about 2,000 inhabitants, or maybe a bit more, and also for agriculture and for gardening and so on. Natural sunlight is collected outside the asteroid by an array of mirrors, of free-floating mirrors, that is collected in this way, and is beamed inside the cave. This is the cave. In the center of the torus, you can see it here in light blue. There is a mirror cone which can distribute and reflect the sunlight, the natural sunlight, of course. We can also simulate a day and night cycle with shutter elements. You can see on the right side the shutter elements. Yes, here on the top of the asteroid. The final goal of this design of a habitat is to generate a closed ecosystem for all the inhabitants. So, yes, of course, there is also the spaceport, which is non-rotating, and which is derived of the former mining station. And here is the so-called rotor joint, where the non-rotating part of the asteroid habitat is divided from the rotating part, from the rotating torus. Now, what is also necessary to avoid thermal overload of the whole asteroid colony, we need a system of heat exchangers which will be installed on the outer surface of the asteroid. So we can get out the overload heat from the colony, from the habitat. Yes, so this was in short words my presentation, and I thank you very much for your attention.
Thank you very much, Werner, for this amazing speech. Of course, you are talking here about technological advanced concepts, and in order to be realized, lots of research and development is required. I have a lot of questions, but before I ask my question, and also before we go and see if our participants would like to ask a question, I would like to comment that maybe someone will ask why
could you stop sharing, please, Werner? Could you stop sharing your screen?
Yes.
Maybe someone would like to ask, why is all that? Why do we have to bring an asteroid to Earth orbit or lunar orbit? We are going to consume extremely high energy propulsion system, the utilization of resources from the moon for that, and then building an entire habitat cave inside this asteroid. Here, I would like to refer the participants for Adriano's webinar that we did 2 weeks ago, complete justification why we have to advance human civilization into outer space. Before I ask my question, and of course, maybe Adriano would like to comment before we do that, we have Diana and Lulwa with us. Maybe if you have a question or a comment about the presentation, of course, we will be happy to hear from you.
It's a quite interesting and informative presentation, Werner. Thank you very much for, and I see that there is a lot of work behind that, of research and designing, and yeah, really an excellent work you did. No, I have just a couple of questions. Well, the first is just a confirmation that I'm asking to you. When you said in one of your slides that there are in 2023 32,000 objects detected, let me say, discovered in
near-Earth objects.
Yeah, these are only the near-Earth objects.
Yes.
So you're not talking about the main asteroid belt.
Yes, we
because
have.
If you include the asteroid, if we include the asteroid belt, then there are millions
in the asteroid belt.
Sorry. Okay.
Millions of them.
Yeah, of course, yes. Yeah, so this was the first one. My second question is, you talk about an advanced propulsion system, advanced propulsion engine based on fusion, nuclear fusion, using S3, etc. My question, of course, a nuclear fusion engine would be very much an interesting thing for going around in the solar system, not only for mining asteroids. But do you think that this is necessary to catch near-Earth asteroid, or could we do it also with existing technologies?
We could do it with existing technologies, but we need to have more time. We would have to have a time of maybe some decades, some 20 or 30 years, so we could do it with existing technology. But if we have just short time, maybe 1 year or 1.5 years or half a year, we have to use, of course, advanced technology.
So now what we can think about is to use Starship to go around the near-Earth asteroids, and to place an engine, of course, because we need engines not only to reach them, but also to place engines on board of the asteroid in order to make it navigate, to transform it in
a Starship. Navigate the asteroids as we want in the future. We want to navigate them. We want to change their course.
And what kind of before the fusion engine will be realized, maybe in 20 years or so, what do you think we could use? Something like a Raptor engine to put it on the asteroid to make it navigate, or something like that?
It will depend on how much time we have before the encounter to Earth. If we have a lot of years' time, we could try this. and it also will depend on the mass of the asteroid. If we have a small asteroid, of course we can do it with conventional methods. But if an asteroid has a mass of maybe 100 millions of metric tons and a great diameter of about 400 meters in diameter, we must need, of course, advanced propulsion systems.
Okay, okay. So yeah, I'm talking because we have two problems with time. One is that a dangerous object coming to hit Earth will need a quick reaction, of course. So this is the first problem of time. And the second problem linked to time is that we have to kick off the industrialization of space as soon as possible. And it would be very much interesting and useful for the whole economy of Earth and the space economy and the civilian space development if we could have some cases of initial asteroid mining before 2030, even by automated machines only or by manned machines. But however, it would be very much interesting, and I think this could be related to our master plan that we are elaborating in the academy, Special Nations Academy.
I think we can target some small asteroids where we will not need science fiction things like I have now showed to you, and we can also do this with more or less conventional systems and conventional rocket systems. And of course, most of the material for our industry, for example, in the Lagrangian points, will come from the moon.
Yeah.
The first decades.
Because we have to learn the lesson by Elon Musk, to work with the technologies we have to reach some goals that are important. Yes. Okay. Thank you very much for your answer.
You are actually touching my question here, Adriano. I was thinking about, of course, when we are talking about advanced concepts, maybe it's a good idea to have a roadmap where we can have small pieces, research and development, small pieces, technology risk assessment, technology need value, general assessment for the technology in order to advance it. And of course, we should assume full industrialization in the moon, in cislunar orbit, and so on. And so my question here, and of course it's relevant also for the youth, maybe can you define topics for masters and PhD that can be done right now by the students as part of this roadmap? Of course, we need to think about it, but maybe general ideas, what we need to do in order to give ideas for the youth, research and development, in order to realize the advanced concepts you are presenting.
Maybe one idea could be that we could send robotic probes to interesting asteroids. I think this could be a first step, and many young people could, of course, be interested in such a thing like a robotic probe. Yes, and I know many astronomers who are on the way to detect nearly every day new asteroids, and most of them are small ones, and we have to choose, of course, to which asteroid we will send robotic probes. So this could be a very interesting field for young people to study.
A good challenge.
Yeah.
Yes. For PhDs works and graduation works and things like that. Yeah, of course.
Yeah, excellent. Any other question from the participants? You can definitely intervene the conservation here. Okay, we will have time, of course, in the future to ask more questions. So, Adriano, Werner, do you have to say? Do you want to say a final comment before we close the webinar?
Well, I was really impressed by this presentation. It's very well done, and as I said before, and we have to go ahead on this track. I think we are on the right track, and of course, this lecture will be online on YouTube and can be watched by the participants to the workshop, and to other people, of course. And okay, so this is my final comment. Thank you very much, Werner.
Werner, do you like to say a final comment?
I appreciate having been here, and thank you very much for the invitation, Grandy.
Thank you very much for your time. Of course, we are happy to have you here. We are building now our webinar series. We will have our next webinar in 2 weeks with Bernard Fong, and he will be talking about space for all. Yeah, Adriano.
No, a last thing, because I see that we have 3 participants, Lalwa, Almetli, Diane Abijur, and sorry,
Anand.
I am confusing with my Anand. Yeah, Nagesh. Would you like to just to introduce yourself very briefly so we can know who you are and see you? Maybe to see your face. Only if you like it. If not, not a problem. Okay.
Yeah, sure. I'll just introduce myself. So I am a electronics graduate. So I've been working in a space startup in India, building rovers and robotic solutions for the moon. So our company's name is called as Big Dipper Exploration, but we are also eventually looking at deep space mining for resources, for like in-space resources for in-space operations. That's about me.
Thank you very much, Anand. Anyone else?
Hello, everyone. I'm Diana Jabur from Jordan. I'm a aeronautical engineering student and interested in Earth-based engineering, and currently working on a CubeSat project, 1U CubeSat in Jordan. And also I've worked with several international research projects, several organizations, and I'm really interested in propulsion systems. And I'm really interested in this project and designing a new Starship concept and to learn more about it. So looking forward for our next meetings.
Thank
Excellent.
you. Thank you very much, Diana.
Lulwa, would you like to say something?
Hello, everyone. My name is Lulwa Midlij, and I'm from Kuwait. I'm a mechanical engineering graduate. Currently, I work as a junior mechanical engineer and different part-time jobs. But I'm really interested in learning new topics, and that's one of the reasons why I decided to join this webinar. And thank you all for your time. It was very interesting.
Thank you. Thank you very much. Okay. So, Ganim, anything else we can close?
No, I am really happy to hear from everyone today. Thank you, Werner, and looking forward for the next webinar in 2 weeks. Bernard will be talking about space for all. Not too technical. It's not going to be too technical, but of course there are going to be interesting topics as usual. And yeah, we are preparing for the event this summer. And yeah, exciting time to come. Thank you very much, and see you all later.
Ad Astra.
See you later, Astra.
Goodbye.
Goodbye.